I welcome all of you to the video lecture series on computational fluid dynamics, development, application, and analysis. This lecture corresponds to the chapter 3 of the companion book on essentials of fluid dynamics and heat transfer for CFD. This lecturing is on topic 2, essentials for CFD. Which is presented separately for essentials of fluid dynamics and heat transfer and essentials of numerical dynamics. This lecture is focused on momentum and energy transport mechanism for the subsection essentials of fluid dynamics and heat transfer. This lecture on momentum and energy transport mechanisms is presented separately for where first I will introduce this various transport mechanism and then I will show you a schematic representation of this advection and diffusion transport in momentum as well as energy conservation. Whenever we talk of in heat transfer as well as in fluid mechanics, whenever we talk of transport of heat and momentum, then there are two transport mechanisms. Although in an undergraduate course, we study fluid mechanics and heat transfer as a separate course. However, both fluid mechanics and heat transfer have the same transport mechanism and both can be studied together in a single course called as transport phenomena. So for both fluid mechanics and heat transfer, there are two transport mechanisms which is presented here. The first corresponding to diffusion transport, the second which is called as advective transport. The diffusion transport corresponds to the random molecular motion of the molecules of a solid or a fluid. In conduction problem, you have a random microscopic motion of the molecule. Whereas when you study fluid mechanics, there is a random microscopic motion of molecules of a fluid. So there are two transport mechanisms. The driver for the diffusion transport is molecular motion. Whereas when this molecular motion move in a bulk, so bulk or macroscopic motion of a molecule, of molecules of a fluid, you don't have any motion of molecules, bulk motion of the molecules in solid. However, in fluid, you can have, although the molecules can have the microscopic motion, but along with the microscopic motion, they can also have a macroscopic motion where a group of molecules move in certain directions together. So when you have a bulk motion, then there is a second mode of transport, and the driver for this mode of transport is the mass flow rate. The driver for this random motion, microscopic motion of the molecules is represented for heat transfer problem in a bulk form by thermal conductivity. Whereas in fluid mechanics, the effect of this microscopic motion of the molecules is represented by the stickiness between the different layers of the fluid called as dynamic viscosity. In the bulk motion, a large number of molecules are moving collectively or as aggregates. When the molecules are moving in aggregates, you cannot stop the random motion of the molecules. Even when the large number of molecules are moving together, when we say onset of flow, there is a molecules in aggregate motion or bulk motion retain their random motion. So, although we are presenting here diffusion and advection separately, but note that when the bulk motion of the molecules occur, when you have a mass onset of flow, when you have a mass flow rate, under that situation also, you have a advection transport also where molecules moves in random motion. So actually the combination of this advection and diffusion is what is called as convection, where along with the macroscopic bulk motion, you have a molecular motion, microscopic motion of the molecules in the random directions. Molecular heat flux includes only conduction heat transfer, whereas molecular momentum flux includes both pressure and viscous forces. The random motion of the molecules in heat transfer results in conduction heat transfer. Whereas the random motion of the molecules in fluid mechanics or molecular momentum flux includes, as I had mentioned earlier, the viscous forces as well as the pressure force. When you have such bulk motions, in the presence of temperature gradient, then you have heat transfer. When you have the bulk motion with velocity gradients, then you have a momentum transfer. What does this mean is, when you have a bulk motion, that what we call as onset of flow, when you have a mass, non-zero mass flow rates, when you have a non-zero mass flow rates in a flow field where there is a temperature gradient, then you have a enthalpy transport which leads to the heat transport, and the onset of mass flow rate in a flow field where you have a velocity gradient lead to momentum transfer rate or momentum transport. Now, here a simple example is shown, first for diffusion, then I'll show for advection, and finally for convection. Let us take an example for, let us suppose you are standing exactly in between ice at 0 degree centigrade and fire at 100 degree centigrade. Note that this spacing is L and this spacing is also L. So if you are standing exactly in between the ice and fire, then if you have a, let us say we are neglecting the radiation mode of heat transfer and there is no flow, so there is no bulk motion. The only motion which is presented here corresponds to a random motion, which corresponds to conduction mode of heat transfer. And we are considering the heat transfer as one dimensional. So under this condition, the temperature which you will experience will be the mean of 0 and 100 degree, which is a 50 degree centigrade, since you are standing exactly in between. This is just to show you the characteristics of the random motion of the molecule or the diffusion transfer. Now let us consider another extreme case, which is called as advection phenomena. Now this advection phenomena corresponds to an extremely large flow in x direction. So let us suppose you are standing again between ice and fire and there is an extremely large flow in, if this large flow is from the positive x direction, if this is the positive x direction and the velocity is extremely large, then you can experience a temperature which is almost same as ice temperature. If the flow velocity is extremely large, which is in the minus x direction from the fire side, then for 1D heat transfer case, you can have with negligible radiation, you can experience a temperature close to fire temperature. Note that it is, when we say pure advection is more of a hypothesis than reality, because in real world situation we cannot have, most of the time we don't have this extremely large flow velocities. It's like that you have so in this case, although you cannot stop the random motion of the molecules, even in an extremely large flow rate situation as this, the random motion of molecules is there, but here we are considering that the advection mode of transport is much larger as compared to the diffusion transport. That's why we are calling this as pure advection heat transfer, which is more of a hypothetical situation than reality. Now, what happens in reality in most of the cases is not pure advection, but a combination of conduction and advection, which is called as convection. So this is an example for one-dimensional convective heat transfer, where you are standing between ice and fire, and instead of extremely large velocities, if you have a velocity, let us say 1 meter per second from the ice side, if there is no flow, you experience a temperature of 40. But if the flow starts from the ice side, let us suppose it's a snow-laden mountain and the wind is coming with 1 meter per second, then you start experiencing cold, and let us say you experience a temperature of 40 degrees centigrade. And if from the ice side, if the temperature is increased from 1 meter to 100 meter per second, you can experience a temperature as low as 10 degrees centigrade. Vice versa, if the flow is from the negative x direction, that is from the fire side, you can experience it. If it's 1 meter per second from the fire side, then you can start feeling more hot, and then it can be you can experience temperature close to 60 degrees centigrade. If it, let us say, it is 100 meter per second from the fire side, you can experience a temperature as large as 90 degrees centigrade. So in reality, this convection is a combination of random motion of the molecule driven diffusion and the mass flow rate based driven advection phenomenon. So it is like this: if conduction or diffusion mode of transport, heat transport is X, advection is Y, then this convection is a combination of, this is like convection, if convection heat transfer is Z, then Z is equals to X plus Y. When we say pure advection, the random motion of the molecule, it's like X is very small as compared to Y. So then in that case, we get a pure advection situation, which is an extremely large velocity case I had shown in the previous slide. So this slide shows the summary of what I had shown through the animation. If you have no flow, then the velocity is zero, flow field is zero, and there is only random motion of the molecule effect. And the effect of the random motion of the molecule is such that you experience a temperature mean of 0 and 100, which is 50 degrees centigrade. Whereas advection, it's an extremely large flow velocity from the ice or fire side. If it is from ice side, you experience almost ice temperature. If it is from fire side, you experience a temperature of 100 degrees. So as I said, that in this case, the effect of random motion of the molecules is negligible as compared to the effect due to the mass flow rate driven advection. This is more commonly found flow with finite velocities for convection, which I had discussed, that depending on the magnitude of the velocity, you can start experiencing more hot or more cold. Now I will present a schematic representation of the advection and diffusion transport in the momentum and energy conservation laws separately. Let us first start with the X momentum conservation law. Note that, as I had mentioned, that the advection transport, the driver, whenever we talk about any transport process, there is a driver and there is a passenger. And in the advection transport, the driver is the mass flow rate. And the product of the mass flow rate with u velocity gives you X momentum flow rate. So in this slide, what I will present, and I had mentioned in my previous lecture, this X momentum flow rate is directly proportional to the surface area, and it acts at the various surfaces of the control volume. So I'll present the X momentum flow rate at the various surfaces of the control volume. This is the X momentum flow rate entering from the left surface of the control volume. Note that there are two subscript of, what is this M? This M corresponds to mass flux, mass flow rate per unit area. If you consider a 2D control volume of height delta y and width delta x, then delta y in a 2D case will be the surface area. So this mass flux, the two subscript, the first subscript represents the direction of mass flux, the second subscript represents the plane in which it is acting. This plane we will call as x, this plane we will call as x plus delta x. So on the right surface, which is x plus delta x plane, this is the, so this second subscript here represents the plane x plus delta x, whereas u is already the velocity in the x direction, and the subscript corresponds to the plane in which it is acting. So here, so this is the product of mass flux with the surface area, which is the mass flow rate, and when you multiply the mass flow rate with the u velocity, this is the rate at which X momentum flow rate is entering. This is the rate at which X momentum flow rate is leaving. Whereas if you consider the top and the bottom surface, note that the mass flux now is in the y direction. Okay, and so in a horizontal surface, the flow, when you consider mass flow rate, the mass flux which is involved is in the vertical direction, because mass flux is always acts in the, we have to consider the mass flux in the normal directions. So here you find that the driver, the mass flux, is in the vertical direction, and the passenger, which is the velocity, u velocity, which is in the horizontal direction. So it is like this: if you're, let us say, standing in a river where the fluid is moving from bottom to top in this direction. Let me show you. Let us suppose you are standing in a river and you are moving in this horizontal direction, and if the flow in the river is moving in the vertical direction, so the flow in the river you can consider as the mass flux which is entering into this control volume, which is perpendicular to the surface area, and you as a fluid particle, as a passenger, you are moving in this horizontal direction. Then you know that this driver mass flow rate push you inward like this. So that's why this is shown as zigzag arrows. Zigzag arrows is due to the fact that the mass flux is in the vertical direction and the passenger, which is the velocity, is in the horizontal direction. So, but the direction of the arrow is basically given by the direction of the u velocity, due to the fact that this mass flux, when you multiply it by surface area, it gives you the mass flow rate, and mass flow rate is a scalar, which is a dot product of mass flux as a vector and the surface area as a vector. So the arrow which is presented here is not vertical, it is in the horizontal direction. This is the rate at which x momentum is entering from the bottom surface of the control volume. And this is the rate at which x momentum is leaving from the top surface of the control volume. Note that here again, the first subscript in M represents the mass flux in the y direction, and here the second subscript is corresponding to the plane. So this mass flux is entering on plane y, this is the plane y, and this is the plane y plus delta y corresponding to this. Here for velocity, this is the subscript corresponding to the plane. This u is at plane y, this u is at plane y plus delta y. Similarly, when you go to y momentum conservation law, the advection transport corresponds to, now at the various surfaces of the control volume, I will show you y momentum flow rate as shown here. So when you consider bottom surface, the mass flux is in the vertical direction. Now here the passenger, which is a v velocity, is also in vertical direction. Both are in the same direction, so the arrow is shown here is in the vertical direction. Whereas for the left and right surfaces, the mass flux mx involves u velocity, because mx is equals to rho into u, and so the mass flux is in the horizontal direction, and the passenger, which is the velocity for the transport, is in the vertical direction. So you get I have shown you by a zigzag arrow. This is the rate at which y momentum is entering from the left surface, and this is the rate at which y momentum is leaving from the right surface. So this represents the y momentum flow rate at the various surfaces of the control volume, where note that these arrows are positive for those surfaces in which the driver, the mass flux, and the passenger, which is a v velocity, they are in same direction. Whereas we show zigzag arrows when the direction of velocity in the mass flux and the passenger, which is a v velocity, they are orthogonal to each other. However, the final direction of the arrow corresponds to the passenger, which is a v velocity, due to the fact that the mass flow rate is a scalar quantity. For the energy transport, so basically I'm showing you advection transport. Note that in all the 3 slides which I'm showing, this is the third slide in continuation. First I had shown you for x momentum, then I had shown for y momentum, and then I'm showing you for energy conservation. Note that in all these 3 slides, what is common is mass flux and surface area. What is varying is in the x momentum, the passenger is u velocity, y momentum, the v velocity. In here for energy conservation, the temperature. So here I will represent the enthalpy flow rate at the various surfaces of the control volume. This is the rate at which enthalpy is entering. No, so let me show you. This is the mass flux. When you multiply by the surface area, it becomes mass flow rate. Mass flow rate multiplied by specific heat multiplied by temperature gives you the enthalpy flow rate. So this is the rate at which enthalpy is entering from the left surface, and this is the rate at which enthalpy is leaving from the right surface. Similarly, from the bottom surface and the top surface. So this represents the enthalpy flow rate at the various surfaces of the control volume, which corresponds to the advection transport, where the driver is the mass flow rate and the passenger is u velocity for x momentum, v velocity for y momentum, and temperature for energy conservation as shown here. Now let us, so first I had shown you separately, now I'm showing you together. So first let us start with, in my previous lecture I had mentioned that in the earlier slide I had shown you advection, the momentum flow rates and the enthalpy flow rate. Now here I am showing you the per unit area term. If you divide those flow rates with the surface area, here we call that as advection flux. So the momentum flux and the enthalpy flux can be represented by a single term which we call as advection flux. So advection flux is a product of mass flux. This C is equals to specific heat in case of energy equation and 1 for momentum equation. And this has two components. I had mentioned that this flux is a vector term, and this A phi x equals to mc phi. I will show you what is this term. Let me show you. For x momentum flux, when you if you consider x momentum conservation, then you encounter x momentum flux. So where this phi is equals to u for x momentum, so this A, now if you substitute phi here, this becomes A vector u. C I had mentioned for momentum equation, it is equal to u. So this becomes, and phi is u. So this A vector phi, A vector u is equals to m vector u. Now this has two components. When here phi is x, for phi is u, so this AUX equals to mxu and AYU is equals to MYU. So these are x momentum flux. So this is the x momentum flux vector which is given, whose components are given by this terms. Similarly, you can substitute C is equals to 1 and phi is equals to V, and you get the y momentum flux in the y momentum conservation. Similarly, when you substitute phi is equals to T and C is equals to Cp, you get the enthalpy flux by this expression. So here I am showing you a generic expression because later on when we go to CFD, we want to develop component by component, and whenever we will develop one component as advection and we will calculate advection flux. So we'll write, when we talk about a component in computer programming, it's a subroutine or a function. So we'll develop a general function for this advection flux where the input mass flow rate will be, mass flux will be common. What will be varying is we'll use it 3 times. So we'll, in the function or subroutine, when we send phi is equals to u, we'll calculate the x momentum flux. When we will send phi is equals to v in the same subroutine, we can get y momentum flux, and for C is equals to Cp and phi is equals to temperature, we can calculate the enthalpy flux. So I'm showing you a generic representation of this advection, the momentum flux and enthalpy flux as an advection flux. So after presenting the momentum flow rate, the enthalpy flow rate, and the momentum flux and an enthalpy flux, now let us move to, I will show you all this fluxes together for x momentum, y momentum, and energy conservation. So this is corresponding to the x momentum equation, where these are the x momentum fluxes in the x and y direction, and these are the y momentum flow rate, and this is the y momentum flux. This corresponds to this AT corresponds to the enthalpy flux, and here you take the product of enthalpy flux with the surface area. This gives you the enthalpy flow rate. So the x momentum flow rate is presented here at the various surfaces of the control volume. Here it's a y momentum flow rate, and this is a enthalpy flow rate. So here earlier I had shown this separately, now I am showing you together, where you can get an idea that for enthalpy transport, the arrow is always normal to the surface, whereas in the x momentum equation, all the arrows are horizontal, and in the y momentum, all the arrows are vertical. This is used in the conservation laws for the rate of change of momentum flow rate and enthalpy flow rate across the various surfaces, flowing across the various surfaces of the control point. From the advection transport, let us move to the next transport, which is a diffusion transport corresponding to the random motion of the molecule. So the random motion of the molecule in fluid mechanics leads to stickiness between the different layers of the fluid. So if you consider, let us say, oil versus water, what you find is the stickiness is different, and this stickiness leads to resistance between the different relative motion between the different layers of the fluid, and the variation in the stickiness between the different fluid depend on the effect of the random motion of the molecule. And this random motion of molecules leads to a flux which is called as stress, viscous stress. Now the viscous forces are represented here by the product of the viscous stresses and the surface area. So for vertical surfaces, the surface area is delta y, and for horizontal surface, the surface area is delta x. And note that here the second subscript denotes the stress. The first subscript represents the plane in which it is acting, and the second subscript denotes the direction of stresses. So note that the second subscript in all these stresses is x. So that's why all this the viscous force are shown in the x direction. So all the arrows are in the horizontal direction. Note that in the previous slide I had shown you for x momentum flow rate, the momentum flow rates in the x direction. Here I am showing you all the viscous forces in the positive in the x direction. So on the vertical surface, the stresses are the normal viscous stresses, and on the horizontal surfaces, these are shear viscous stresses. This is for viscous forces in the x direction. Similarly, you can have viscous forces in the y direction, where all the arrows are in the vertical direction. So note that the viscous forces in x direction consist of sigma xx, sigma yx, whereas viscous forces in the y direction consist of sigma xy and sigma yy. For an incompressible flow, if you are considering the x momentum conservation law, then the diffusion transport is presented here as for viscous forces in the x direction. The viscous stresses, although general expression in terms of velocity gradients from fluid kinematics, sigma xx equals to 2 mu del u by del x, and sigma yx equals to mu del u by del y plus del v by del x. But for incompressible flow, this relationship between stress and strain and the velocity gradient gets simplified, and for an incompressible flow, the sigma xx can be, instead of 2 mu del u by del x, it can be expressed as mu del u by del x, and sigma yx instead of mu del u by del y plus del v by del x. If you apply continuity equation for incompressible flow, instead of 2 here, you get only 1 here, and this del v by del x disappears, because when you apply incompressible flow mass conservation, which leads to del u by del x plus del v by del y is equals to 0, you can get a simplified form of viscous stresses for incompressible flow, which is shown here. The reason it is shown here is that this has certain commonality, which I will present in the next slides for viscous stresses in the y direction and the conduction heat fluxes. So the diffusion flux, which corresponds to viscous stresses in the x direction, sigma dot I, which is basically equal to sigma xxi plus sigma yxj, is equals to mu del u by del x plus mu del u by del y. So these are the expression for sigma xx and sigma y in terms of velocity gradient, and it leads to this. Similarly, if you consider viscous forces in the y direction for an incompressible flow, although sigma xy has mu del v by del x plus mu del u by del y, and this is equal to 2 mu del v by del y for a general case, but for incompressible flow, this also gets simplified, and you can write sigma xy instead of here you get 2 mu del v by del y, and sigma xy is equals to mu del v by del x plus del u by del y. So in this del u by del y, and one of this, it doesn't have a 2, and this 2 gets simplified as shown here. And the diffusion flux in the y direction is given by this expression as shown here. Okay. Now the energy conservation law, conduction heat transfer rate, is presented in this slide, where conduction fluxes are given by this expression, where the conduction flux is equals to minus k dt by dx, and conduction fluxes in the y is equals to minus k dt by dy. All of you know this from the Fourier law of heat conduction. So the diffusion fluxes for the temperature is given by the conduction fluxes, which is equals to minus k grad of T. So from the previous 3 slides, you can note that the way the expressions have been written, the normal gradient of u velocity gives the viscous stresses in the x direction, the normal gradient of v velocity gives you viscous stresses in the y direction, and normal gradient of temperature gives you the conduction heat fluxes. Once we realize this commonality, then later on in CFD, we write a subroutine or a function, and then we develop one component and use it 3 times for calculating the diffusion term of the x momentum, y momentum, and energy equation. So in the earlier slide, I had shown you the viscous forces and the conduction heat transfer rates. In this slide, I am showing you a generic form of the diffusion flux, which is represented here by d phi vector, which is where this gamma phi is called as diffusion coefficient, which is equal to mu for the viscous component, and this is equals to k for conduction heat transfer rate, where this d phi x equals to gamma phi del phi by del x, and v phi y is equals to gamma phi del phi by del y. The viscous stress in x and y momentum equation is given by this expression, where this diffusion flux vector for x momentum equation is given by the normal gradient of u velocity. Note this del u by del x, x on the vertical surfaces. This is equal to sigma xx. This is equal to sigma yx. This is a shear stress. Similarly, this is for the y momentum equation. This is the conduction heat flux. dt corresponds to the conduction heat flux, and you know that this is represented by minus k of grad of t. So note that here this is sigma xx, this is sigma yx, this is sigma xy, and this is sigma yy. And these two are normal stresses. They act on the vertical surfaces. This acts on vertical surface. This acts on the horizontal surface. And this is the conduction flux, which always acts normal. Note that all the arrows for, I'll show you in the next slide, the direction of arrows for the x momentum, y momentum, and energy conservation. So here you can see that this is corresponding to the viscous forces in the x direction, where all the arrows are in the horizontal direction, which is the x direction. This is corresponding to the viscous forces acting in the y direction, where all the arrows are in the vertical direction. And this is corresponding to conduction heat transfer rates, where all the arrows are normal to the surface area. So in this slide, I am showing you the random motion of molecules based momentum transport for x momentum, y momentum, and energy equation. As I had mentioned, note that this sigma is a second order tensor, which is given as sigma is equals to sigma xx, sigma yx, sigma xy, sigma yy. Now when you take, here it is shown sigma dot I, and here it is shown sigma dot j. I am just showing you the operation of this second order tensor viscous stress with I. When you take a dot product with I, you basically get the first column in a vector form. So sigma dot I will be equal to sigma xxi plus sigma yxj, as shown here. Sigma dot I is equals to sigma, take the first column as shown here, sigma xxi plus sigma yxj. Whereas if you take sigma dot j, you get sigma xyi plus sigma yj. This is the operation of a second order tensor with a unit vector, which converts the second order tensor to a vector. Now finally, I am showing you for each conservation law, the advection transport, which is where the driver is the mass flow rate, and the diffusion transport, which corresponds to the random motion of molecules. So for x momentum equation, these are the x momentum flow rates, which are presented where all the arrows are horizontal. Here also, this corresponds to the viscous forces in the x direction, where all the arrows are in horizontal direction. So with this, we calculate we consider the momentum flow rate, x momentum flow rates on the various surfaces, and from this we calculate the rate at which x momentum flow rate is leaving the surface of the control volume. This is used to calculate net viscous forces in the x direction. Similarly, for y momentum, this is the rate at which y momentum is leaving the control volume. This corresponds to the viscous forces in the y direction. This gives us the rate at which enthalpy is entering across the surface from the various surfaces of the control volume, and this gives you the total heat gained by conduction heat transfer. The advection flux, as I had mentioned, it's basically expressed for x momentum when we take the dot product of the momentum flux. This m vector u vector is a second order tensor momentum flux. When we take a dot product with I, you get this. And the operation is similar to the stress which I had shown in the previous slide. This also has in a 2D Cartesian coordinate system. It also has 4 components, and when you take a dot product similar to what I had shown in the stress, you get m vector u. And for momentum flux in the y direction, y momentum flux, you get m vector u, and this is the enthalpy flux. And these are the expression for the diffusion flux, the viscous stress in the x direction, viscous stress in the this will be the y direction, and this is the conduction flux. Note that finally, although momentum conservation law is a vector law, but since we applied component by component, the flux, which is a second order tensor, finally when we apply in a component, the flux gets converted into a vector. With this, I had come to the end of this lecture, and the details of this can be found in the chapter 3 of this book, Introduction to Computational Fluid Dynamics, Development Application Analysis. And you can also get the supplementary material corresponding to the books, which corresponds to fluid dynamics movies, computer programs, and colored figure corresponding to this book. Thank you for your attention.